So, hi everybody at the Temporal Graph Reading Group. Today we have Manuel Dileo. He's a PhD candidate at the University of Milan working in the Connets Lab. His research focuses on the intersection between network science and graph machine learning, with a particular emphasis on temporal and heterogeneous graph reasoning. And he has been a visiting researcher at the University of Edinburgh, where he worked on temporal knowledge graph reasoning. And today he's going to present tensor decomposition for temporal knowledge graph reasoning from completion to forecasting. And with that, I will hand over the mic to you.
Okay, thank you, Julia. Hi, everyone. Thank you, Julia, for inviting me, and thank you, all the organizer, for having me. It's a pleasure to be here. So today I will give this talk about tensor decomposition models for temporal knowledge graph reasoning, and I will touch two of our works that I've done in collaboration with my research group, that is the Connets Lab in the University of Milan, and also Professor Pasquale Minervini from University of Edinburgh. So if I can, okay. Let me start with just some background. Temporal knowledge graph, I'm sure you know them, are basically graph structural knowledge bases where the knowledge about the world is encoded in the form of timestamp relationships. So in the end, you will have a collection of tuples like subject, predicate, object, timestamp, where subject and object are nodes, entities. The predicate is a relation with a semantic, and the timestamp represents when a certain relation happened. So for instance, you can have Obama criticize Russia in a certain date. And when reasoning on temporal knowledge graph, one of the most crucial tasks, since it's able to allow to capture the dynamics of the temporal knowledge graph, is link prediction, in which you want to predict links typically at precise timestamps. So a model needs to answer queries like subject predicate question mark timestamp or question mark predicate object timestamp based on the knowledge graph data you have. And you need to distinguish two different settings you can have: the temporal knowledge graph completion setting, where you want to predict missing links in the temporal knowledge graph history. So you know the entire history of the temporal knowledge graph, you want to predict just missing links at precise timestamps, or the temporal knowledge graph forecasting task, in which you want to predict future links in the temporal knowledge graph, given the knowledge graph up to a certain time t. So of course, these two settings leads to two different big families of methods to handle the task, and the performance of these methods can be directly compared for fairly comparison. And there are several approaches actually to extract, learn, and predict information over temporal knowledge graph. For instance, there are solutions based on message passing with sequence modeling like RGCN, transformer-based architecture in the sense that they use attention-based mechanisms to leverage the temporal information, or even directly LLMs to answer queries as the one I showed before. Copy generation mechanism, as well as exact algorithms based on extracting logical rules and do inference on them, or heuristic baselines that actually work quite well, like leveraging recurring facts. But in this presentation, we will focus on tensor decomposition models that are very simple neural models, in which basically embeddings for entities and relations are just lookup matrix of learnable parameters that are adjusted, minimizing a certain loss function. So there is no kind of sophisticated architectures behind them. They are just embeddings of lookup metrics that are combined through linear scoring functions, typically to obtain link prediction scores, like using the dot product. And they're, for these reasons, very fast to train and evaluate. So of course, the evaluation step is a bit of a bottleneck if you want to use the ranking-based formulation of link prediction task. But if you have a very, very big graph, of course, you can always do negative sampling. But in general, they are very fast to train and evaluate, since you need only to compute a linear scoring function that is linear in the number of dimensions and does not depend on the number of entities and relation you have. And actually, this is interesting because it has been shown in the literature that they can reach, despite being very simple, a very competitive performance on static knowledge graph reasoning tasks like knowledge graph completion or even complex query answering when they are carefully trained and tuned. So when you choose and tune the hyperparameters, when you choose a suitable embedding dimension, and when you do regularization of them. And this is shown, for instance, in two works I cited here, one by Ruffinelli and other colleagues, that is called You Can Teach an Old Dog's New Tricks, in which basically they've shown that even very simple models like rotate E or trans E that were proposed like more than 10 years ago, that is like a century for AI research, can work pretty well when they are regularized and carefully tuned. And even the work by Lacroix, they show that basically complex achieve state-of-the-art performance on knowledge-based completion task when this is, again, carefully training tuned. So basically, the main research question behind our works was to understand if tensor decomposition methods can achieve state-of-the-art performance even in temporal knowledge graph reasoning, retaining their efficiency advantages compared to, for instance, message passing solution. And to do it, basically, we focus on TNT complex. This is an extension proposed by Lacroix of complex for temporal knowledge graph, in which basically they just add an embedding lookup matrix for timestamp embeddings. So in the end, you have a scoring function that is the real part of the multilinear dot product between the embedding of the subject, the predicate, the conjugated complex of the object, and the timestamp. And basically, the embeddings are just obtaining by minimizing the instantaneous multiclass loss. So the first term is related to the positive examples, and the second term is related to all the negative edges you can obtain by head or tail corruption. And then they also have a penalty term that regularizes the embeddings to avoid overfitting, and that is really important to have because it can really boost the performance of these kind of models. And it's typically performed using a nuclear tree norm because empirically it has been shown that it works better than more standard solution like L2 or L1. And basically, as I said, we will present two works. One is already published and it won the Best Paper Award at ESAN this year, and it's called Enhancing Neural Link Predictor for Temporal Knowledge Graph with Temporal Regularizers. It's also the work that is linked on the TGL website, in which basically we focus on temporal knowledge graph completion, and we show that TNT complex can boost its performance with a tuned temporal regularizer. And on the other hand, we have an extended version of this work that is actually submitted to a journal. So we present some preliminary result, or in general, preprint result, in which we focus on temporal knowledge graph forecasting. And basically, we show that tensor decomposition can work pretty well even for doing forecasting. And so let's start with the first one. The idea of temporal regularizer is just to add a simple penalty term in the loss function. So in the end, you will have three penalty term, one related to the task, that is the multiclass loss, and is related to link prediction, of course. The embedding regularizer with a parameter lambda 1 that rule the strength of the embedding regularization and is performed using the nuclear tree norm. And then you have another penalty term related to temporal regularizer with a parameter that tune the strength of the regularization as well. And the idea is to encourage factorization models to learn basically transformation for timestamp embeddings that capture certain specific properties that are useful for real data set. And actually, some temporal regularizers have been proposed in the literature, but the impact of how to choose them or how to tune them is poorly understood. So typically, there are no information in the paper about how to carefully tune temporal regularizers. And typically, new temporal regularizers are proposed together with the new architectures, new tensor factorization methods, and they are not tested on previous factorization methods and vice versa. So or even the new models are not tested with old temporal regularizer. So basically, the first work systematically analyzed a wide array of different temporal regularizer for temporal knowledge graph completion using TNT complex. And so I want just to review the three big families we have tested. The first family of regularizer are the smoothing regularizers, in which you want to basically take advantage of the fact that most entities behave smoothly over time, so they act very similar in closer timestamps. And so you want to encourage the timestamp embeddings to be similar for closer timestamp. And basically, you can do it by simply imposing a norm over the difference between the timestamp embedding of two following timestamps. And it has been shown and tested in the literature using only nuclear tree norm because it's the one that works well, or even on the embedding regularizer part. But in our work, we basically investigate its impact considering a wide class of norms in the LP and NP families, with the idea that even the norm can rule the strength of the regularization. And then we have linear tree that is proposed in this work in 2021 at NACL, in which basically they add like a bias component in the timestamp differences, that is the matrix of learnable parameters capital lambda, with the idea to encourage that even distant timestamp have distant embeddings in a certain sense. And for the scope of this work, it's interesting to notice that this kind of score, this kind of norm, can be also interpreted as a kind of score in the mode or in the world of tensor decomposition methods, like the score of triples tau plus 1 follows tau, where the embedding of tau plus 1 and the embedding of tau is given by the timestamp embeddings, and the embedding of the predicate follows is given by the bias component, the capital W matrix of vulnerable parameters. So from this point of view, it's like you are computing the average score of these triples with this regularizer. So you are like explicitly modeling the timestamp dynamic to the predicate follows. And so at this point, you can also propose a regularizer based, for instance, on recurrent neural network that implicitly learn the temporal dynamic, acting as a temporal regularizer in which you want basically to start with a certain hidden state, and then you process the timestamp embeddings one between each other in a sequence way, and you can obtain this way how to generate timestamps, and in the end, in a certain sense, learning implicitly the temporal dynamic between them. So basically, in this work, we test smoothing, linear tree RNN regularizers on TNT complex, and we focused on temporal knowledge graph completion task, in which basically you have a random split of data set in train, validation, and test tuples, and queries as like subject predicate question mark timestamp, but all the timestamp are known since you're only interested in predicting missing links. And you can adopt the filter at the mirror reciprocal rank setting. So you filter out, when you compute a ranking-based matrix, only the edges that exist at the query time, not all the positive edges. And basically, in this case, competitors are mostly based on tensor decomposition techniques because they work well, plus different strategies to handle the temporal dimension, like temporal regularizer, as in our case, or just timestamp embeddings without regularization, or RNNs, attention-based, or temporal message passing. And we focused on 3 different datasets that are actually 3 very well-known datasets in the literature that in this case are split at random. ECWS that are event networks, so they contain facts extracted from geopolitical events every 24 hours, and Yago that is an encyclopedic source of events with timestamps. Some facts has also missing temporal information, so it's really interesting. It is also coarser time granularity because it's a granularity of yearly timestamps, and the time span is also huge with respect to ECWS. So this is a big table of results. I want just to highlight some of the most important. In this table here I just reported the mirror reciprocal rank performance. And as you can see, TNT complex, our version with regularizers can outperform the other competitors, can also achieve better performance than the original version of TNT complex proposed in 2020, as well as the static version complex. But also it works better than other solution that combines tensor decomposition with different strategies to handle time, like RNNs, timestamp embeddings, attention-based mechanism, and GNNs. Regarding how to choose the temporal regularizer, here we reported, for instance, the mirror reciprocal rank performance over different time regularization weight for the different temporal regularizers on the 2 ECWS datasets. And as you can see, the blue line is the performance related to the original version of TNT complex, and there are 2 solutions that outperform for any kind of time regularization weight the original solution, that are based on linear tree or nuclear norm based or N4. On the other hand, RNNs actually it seems to struggle in this setting to generate a very long sequence of timestamps and in general to capture the dynamics implicitly. And so we can switch to the second work in which instead we focus on temporal knowledge graph forecasting. So in this case, queries are always like subject predicate question mark timestamp, but all information up to a certain timestamp is known. So accordingly, dataset in this case is split chronologically over time in train, validation, and test facts. And typically in benchmarks, models are allowed to use information contained in the validation set to answer queries at test time, to like avoid an information gap between the train time and the test set time, since the data set, as I said, is split chronologically over time. And in this case, state-of-the-art techniques are not based on tensor decomposition. Actually, they are not even explored mainly, and we will see how and why. And they are mostly based on message passing, like ReGCN or ReNet, plus sequence modeling. And luckily for us, we can still use the filter setting. Well, basically, we observed that the potential of tensor decomposition for temporal knowledge graph forecasting is heavily underexplored compared to temporal knowledge graph completion for a silly reason, actually. They are methods that just leverage lookup tables, so they cannot work in inductive settings. So they cannot generalize to new entities, they cannot generalize to new relations, but this is not a big problem for temporal knowledge graph. You always work with the same set of relation and with the same entities, but they cannot even work with unseen timestamps, since you only rely on lookup tables. And so if we have just a matrix of learnable parameters, you cannot learn from future timestamps that you cannot see. And on the other hand, of course, tensor factorization does not compute like node and edge representation dynamically. They just compute scores. And so they can easily include tuples like from validation set without cheating, so that is, without training on them. And this is when you compare tensor decomposition methods, as in this presentation, with standard benchmark in the literature, it should at least be noticed for fair comparison. And so let's see how we can easily, for instance, generalize to unseen timestamps in terms of decomposition methods. Well, basically, we act in two simple steps. The first step is just for remove some noise and like ensure stability over different granularities and data sets. We mapped each discrete timestamp because typically we have dates or even progressive integer IDs to real scalar values that are normalized. So we use first the elapsed time from a certain reference point, for instance, the starting date of the data set, and then we normalize this value, continuous value we obtain by removing the mean and divided by the standard deviation over the train timestamps. And well, then we can basically modify the scoring function of the anti-complex to include a parametric encoding function that generate timestamp embeddings for any scalar t, instead of having a embedding lookup matrix. And regarding how to choose the parametric encoding function, of course, you can opt for different solution available in the literature, sinusoidal position encoding, or even extract Fourier features using just a linear layer to project a scalar to a timestamp embedding, the time to back approach, or a radial basis function network. And in the end, we opt for the latter, actually, and we will see why. And this is a default choice in our code. So you basically, if you want to use our code, this is available on GitHub. You go with radial basis function network, but of course, from a code perspective, you can easily choose and change the parametric encoding function for timestamps. Well, basically, the normalized real value timestamp is mapped to an embedding through a set of k-radial basis function combined with a linear layer. So basically, each of the radial basis function is a bell-shaped function. I don't want to insult your statistical knowledge. And basically, the center and the radius are learnable parameters of each of the radial basis function, and k is chosen to be equal to the embedding dimension of your tensor decomposition methods. And we actually choose this solution as default because radial basis function networks are known to provide like smooth, continuous, and learnable representation of time that are actually very nice properties for temporal knowledge graph, because it has been shown, even thanks to our work on temporal regularizer, for instance, that most of the entities behave very smoothly over time. So you need like a representation for timestamp that is moved over time. And there are also other works related to, for instance, heuristic baseline for temporal knowledge graph forecasting, when it has been shown that just using the directly recurrence of edges can produce very actually good results. So you want something related to timestamps that is capture local temporal patterns, and radial basis function works really well for it. And as you can see, even from the graph here, we plotted basically the radial basis function for timestamp embedding, for instance, equal to k equal to 5 over different scalar values between 0 and 1. And as you can see, basically you change very smoothly over time the representation of timestamps. And regarding the evaluation, experimental evaluation here, we consider the 5 most well-known data set in the literature to do temporal knowledge graph forecasting benchmarking. 2 data sets coming from ECWS that are differently from the one considered for completion. And I recall that in this case, the data set are split chronologically over time instead of random. And then we have GDLT, that is another event network that records like global news events extract from news feeds or newspapers and so on every 50 minutes. So it exhibits very high temporal granularity and density. And then we have again Yago, that is an incorporated sources, and even in this case we have Wiki that are derived even from Wikidata. And in their case, they are basically mostly based on like causal relationship and long-term patterns in a time span that is wide respect to the other data set. And here present some results in the multi-step forecasting. So you are basically interested in predicting future events at any timestamps, not just in the following timestamp. And notice that all the competitors that we consider that are the one available in the benchmark by Julia Castinger, that is here, well, basically are RGCN and VNet that are based on message passing plus sequence modeling, copy generation mechanism, and logic rules. All the competitors leverage validation set information in this case and in this table, whereas tensor decomposition methods do not leverage them. And as you can see, especially on CWS datasets and GDLT, so the event networks, tensor factorization methods are very strong alternative for temporal knowledge graph forecasting. Even the static version of complex can work really well and achieve comparable performance. And on GDLT, like our version of TNT complex with radial basis function network, achieve a stronger performance than the other methods. However, it struggles a little bit on the two encyclopedic sources. This could be related to the fact that in this case, you need, as I said, to capture more long-term relationship or causal relationship over time. So you need really to understand the logical rules following the evolution of the network. And in fact, T-logic works really well, and even the RGCN. However, we have even some result in which some methods actually reported the result without validation, without using of validation set information. And as you can see, the two models that report this result exhibit a performance drop on all data sets when they are evaluated under this like more restrictive setting, whereas our models, of course, does not exhibit any drop since they are basically the same models. And as you can see, notice that the huge performance drop you have is on Yago, that is the data set in which tensor decomposition struggled the most. So maybe this could be also be related just to the information gap between the train set and the test set. And actually, I don't want to roast anyone and do this thing or all that kind of stuff, but there were some tensor decomposition result in previous benchmarks reported, like in the work by Lee et al. In 2021 and another work in 2022, where they report performance for complex methods and TNT complex. But as you can see, our version of complex and TNT complex achieve very higher performance across all metrics compared to the one previously reported. Unfortunately, we don't know all the technical details of their experimental setup, but we can suspect that they do not use regularization in the embedding part, since, as we said, is a really important part for to add as a penalty term in the loss function to tensor decomposition methods. But the original version of complex basically do not use this kind of embedding regularizer and is not carefully tuned as in the work by Lacroix in 2018, for instance. So basically, this is just to show that complex and TNT complex, if they are really carefully trained and tuned, can achieve significantly higher performance. And we also conducted some hyperparameter analysis. I reported just the result for two hyperparameters that are embedding dimension and temporal encoding function. So in the left side, we have the figure for the embedding dimension, and we have the mean reciprocal rank performance spanning over different embedding dimension. And as you can see, for all the data set, even using like 100 as embedding dimension, you can achieve very good result. And on the other hand, we have a comparison of different solutions to do timestamp encoding. So in yellow, we have radial basis function network, but we have also considered other solutions like time to vec, positional encoding, linear function, and Fourier features. And as you can see, even empirically, radial basis function network outperform the other common solution to do timestamp embeddings. So the key takeaways up to now are that tensor factorization methods are really simple and fast neural link predictors, fast to train and evaluate, and really simple models without any sophisticated architecture behind them. They are just linear function computing on embedding of lookup metrics of embeddings. And basically, by carefully training and tuning them, they can reach comparable performance with other competitors, both on temporal knowledge graph completion, when we show that temporal regularizer can enhance the performance of TNT complex, and even on temporal knowledge graph forecasting, that maybe is the most interesting part, which are a very strong alternative compared to other solutions. And just because we are in a reading group, I want to conclude with some perspective and future direction. So we have done this mainly for the purpose of benchmarking, but actually the tensor factorization methods are interesting also for other interesting facts. The first is related to the fact that actually they can do inductive reasoning. There is a nice paper by colleagues at UCL in 2022 in which they show that basically tensor factorization methods are implicit GNNs. Just to give you an idea, basically they study in detail the optimization process of tensor factorization methods. So when you fix a certain tensor factorization function like the dot product with dist mult and a certain optimization process like you use stochastic gradient descent, if you focus on the optimization process, basically, if you have the ranking-based problem, you are doing implicit message passing given by the backpropagation graph over the structure of the network. And so in this way, you can map the factorization model to an equivalent GNN layer. And so once we have the equivalent GNN layer, you can allow to do inductive reasoning, of course, and even use, for instance, GNN explainer and graph explainability techniques in general, and so on and so forth. And there is also another work I want to highlight, work by Lorenzo Loconte and other colleagues from University of Edinburgh, in which they show that knowledge graph embeddings based on factorization techniques and tensor decomposition models are probabilistic circuits. And basically, this is interesting because they show how to add logical constraint and how to scale more gracefully even to big graph. These are really important, for instance, to network science, that is the part of our research that is focusing on doing network analysis through graph theory and analysis in general of the networks of complex systems. Because using this reinterpretation, they show that basically they can guarantee logical constraints over the knowledge graph structure that are satisfied by design. So when you compute scores for facts that does not satisfy certain logical constraint, you obtain a probability of 0 by default. And for instance, you can add external knowledge base. For instance, this relation cannot exist at that timestamp. Or for instance, these two entities are not active in that timestamp, or there must be this relation at this timestamp, and so on and so forth. And they can also propose, thanks to this interpretation, a new version of knowledge graph embedding methods based on probabilistic circuit that scales even more gracefully than the original tensor factorization models on graph like with million of entities and a billion of edges. And this is really important, especially for network science community where we have a very, very big graph, but even for temporal graph learning communities, this is an important issue to solve, of course. And oh yes, I forgot. Yes, I have also a little shameless promo time. We are actually organizing a ESAN special session next year that is dedicated to learning and reasoning over knowledge graph and even heterogeneous graph in general. So if you basically fancy Bruges, you want to submit something to drink beers, eat mussels, and in the end, if there is time, even talk about knowledge graph reasoning, well, you can do it by the 19th of November, and we are happy to read about your contribution. That's all. Thanks for your attention.
Thank you very much for the presentation. Do we have any questions from the audience? Feel free to type them in the chat or speak them out. For now, I can start. So I was very surprised by the results that you showed in page 37, I think, when you showed that the static complex is already pretty competitive with the other methods, right?
Yes. Yes, yeah, consider that, for instance, the CWS datasets are known in the literature to be very entity-centric. So typically do not contain long-term relationship or long-term causal patterns over time. So they're very entity-centric in the sense that if two entities are active in a certain time set, they will probably interact one each other. So in this case, you have a static model like complex that mainly focus on the behavior globally of the entities. So it can work really well. This is our intuition why even the static version can work really well, especially on the CWS.
I think that makes a lot of sense, especially also in the multi-step forecasting setting. And can you go to the next slide where you compare to the originally reported complex results?
This one, yes.
Yes, exactly. So that was also surprising to me. And I think you said that it might be due to the regularization, as the originally reported complex results are that much worse than yours, right?
Yeah, because basically even in their papers they cite the 2016 version of complex and the first version of TNT complex, where basically the main idea to propose was the idea of taking complex embeddings and doing the scoring function as the real part of the multilinear dot product and so on and so forth. And they do not do like embedding regularization in that work. So basically, it was like thanks to the work by Ruffinelli and thanks to the work by Lacroix in the 2020 and 2018 that they studied to carefully tune how to carefully tune these methods using embedding regularizer and other techniques to obtain very good performance. So we suspect that they just use the default version, and this is okay, of course. But then there are other works that just carefully train and tune these models, and using their suggestions, basically, we can boost a lot the performance. Yeah, and this still holds for knowledge graph reasoning, static knowledge graph reasoning in general. If you see the paper by Ruffinelli or Lacroix.
It's very interesting. It's actually quite straightforward, the thing that you did, because it's somewhat simply and nice.
Yeah.
So it's really cool to see that your results are that good. I have another question while I'm still unmuted. You do not have by any chance also single step prediction results?
No, not now.
Okay.
No.
If you ever happen to have them, I'm interested.
Okay. I can, maybe you need just to change like the way you do the evaluation and the way you split the data, because since they are mainly like based to do temporal knowledge graph completion, it's easy to do the multi-step forecasting task, whereas you need just to change a little bit the evaluation pipeline to do the single step forecasting task. But yeah, it will be really interesting. Even because there are other models, of course, that do just single step forecasting. So
yeah, exactly. Okay, thank you.
Sorry to interrupt you. I have just one question regarding the empirical evaluation. I'm wondering, have you ever compared this method with any graph neural network-based baseline?
Yeah, actually, ReGCN and ReNet use graph neural network to process the overall topology of the network. So they are in the most straightforward way. They are like stacking graph neural network layers with the GRUs. It's not like this simple, but this is the main idea. So actually, in this slide here, you have the comparison between graph neural networks plus RNNs against tensor decomposition methods. So you can see the comparison here. The first two lines against ours, basically.
Okay, thanks very much. I'm also wondering, there are several simple but very sufficient design for link prediction for the not temporal graph, just the old graph benchmark. For instance, like the PageRank score and the common neighbor, they are very sufficient design for link prediction. I'm wondering how does it perform in temporal graph link prediction?
It's a very nice question. We actually done it in a work published at ISAN 2 years ago that is called the Link Prediction Heuristics for Temporal Graph Benchmark, where we applied basically a heuristic based on common neighbors and preferential attachment on the TGB dataset, the standard one. And we have shown that actually they perform quite well, but not so well. They perform like better than TGN, but even EdgeBank perform better than TGN. So it's not really interesting, but yeah, on temporal, maybe you can think about something to like extend the heuristic baselines, like based on common neighbors, to the temporal dimension. That could be a very nice line of research. And yeah, we have done something like the first step towards this solution with the link prediction heuristic for temporal graph benchmark paper. But yeah, it could be a really nice research project, and even for temporal knowledge graph could be really interesting. Of course, you need to like combine the common neighbors based on different relationship, or you need to do something for the heterogeneity part as well. But it could be, yeah, really interesting to benchmark even these very simple and heuristic models, because the problem was that in benchmarking result, typically we have only deep learning models that, okay, they works in a certain way, but then they are mainly outperformed by very simple solution, rule-based solution. So yeah, could be really interesting to extend this discussion even on temporal knowledge graph.
Oh, thank you so much. Can you please tell me the name of that paper and benchmark paper you published 2 years ago again?
Link prediction heuristics for temporal graph benchmark.
Okay, thank you so much.
No problem.
All right, I think if we don't have any other question from the audience.
I will just add a random remark on that, just to kind of, I find it very interesting. So if you think about all the graph foundation model stuff talk recently, right? There's a lot of buzz about graph foundation models and stuff. But if you think about their definition, so model that is pre-trained, quote unquote pre-trained, directly applied to a data set, requires no hyperparameter tuning or like expert to pick, how many layers, how many neurons, and you can just deploy the model, and then it works, and also scalable. These definition, outside of the pre-training part, let's throw away that. These definition all fit something like a common neighbors heuristic. So from a sense, these classical methods are already foundation models because literally you can run common neighbor on anything. You can run edge bank on anything, right? So like, but of course they don't give you the best performance, but not necessarily the best performance. Sometimes they do actually, but this is like so I think like investigating on the heuristics and having a good set of test for the heuristics before you claim your model is state of the art on some benchmark is is very important. And also these heuristic ones are usually much more interpretable than the GNN ones, because GNN ones just give you some probability and then it does well, doesn't do well, but like you don't know what's going on, right? So so just random remark on that.
Yeah. That's a very interesting discussion. And even Ultra, for instance, if I want to cite just some graph foundation model, it has been shown that they can compute, for instance, page rank and other kind of metrics on graph thanks to the neural Merman-Ford algorithm. And it's really interesting, to
Yeah, I think
understand
like
this.
the theory of foundation model is a different, very interesting direction. Yeah, so that's all I want to say. I also want to do a little marketing message, but not directly for knowledge graph. But so we have the TGM library that recently released in beta. We'll have a talk sometime in the reading group, not confirming time yet. But basically, it's a new library. So if you play with these models and you are tired of DigiLib, and you should try it out. So it's here. And also, like, if you want to add heuristic, try out these heuristic ideas. You can try it out on TGM, and you can just merge in your model with a PR. So it's very easy to try. Yeah. So, but we'll discuss more in detail in the future talk on those.
Cool.
Okay, yeah, thanks for the talk.
Thanks to you for inviting me.
All right, then. Thank you very much, and see you at some point in an upcoming reading group. Bye-bye.
Yep. See you. Have a
Bye.
nice
See
one, everyone.
you.
Thanks.
Have a nice evening.
Bye.